So far, you guys have done polars. So you did polar coordinates last week and you've done polar graphs this week. The other topic that goes in this chapter are vectors. So vectors are a quantity that have both direction and they have a magnitude or a size. So for every vector, you're going to have to figure out the degree of the direction and the magnitude or the size of it. If I were in class right now, we would watch this video, but we're not, so I'm not going to. But if you remember, if you're familiar with Despicable Me, there is a villain in there named Vector, and he possesses these properties and talks about them in this little clip here. It says, let's draw a vector to represent an airplane flying with a velocity of 300 kilometers per hour in a northeasterly direction. So the speed is our magnitude, the size of it, it's 300 kilometers per hour. The direction I'm saying is 45 degrees, and here's why. If you're going completely north, going up and down, that'd be 90 degrees, straight up. If you were going completely east, that would be at 0 degrees, because you'd be going like side to side, essentially. So we're going northeast, so that's halfway in between 0 and 90, which is where the direction of 45 degrees came in. So just think of this as a coordinate grid here. You always are going to have a start and an end to your vector. And this angle that it makes with the horizontal is 45 degrees. And our magnitude, or the size of our vector, is the 300 kilometers per hour. So let me show you another example. Like I said just now, we could put this vector on the coordinate plane, but it really doesn't matter where we put it because we can put it in like an empty space. Regardless, your vector just has to show the direction and the magnitude. But generally, we place the initial point of the vector, which they call the tail, at the origin if you're putting it on the coordinate plane. And then the head, or like where the arrow is on your vector, they call that the terminal point. So the initial point is the tail at the origin, and the terminal point is the head. And it's represented by the arrow. All right. So a lot of your questions are going to ask you to find the horizontal and vertical components, or you'll see it say like, what is the component form of this vector? And it's simply looking for the horizontal and vertical components. So for a lot of this, we're going to be using Pythagorean theorem or trig to get the values that we need. So again, it says, let's find the horizontal and vertical components of our airplane's vector so we can find the coordinates of its head. So we're trying to figure out, where is this up here? So the horizontal component, if I make this into a triangle, the horizontal component I could call X, and the vertical component here I could call Y, and then I could use trig to figure out how long those are. So if I were to use trig, this horizontal component would be the adjacent side, and the 300 is my hypotenuse. So I could write the trig equation that the cosine of 45 equals my adjacent side, which I'm calling X, over my hypotenuse, which is 300. Put that in your calculator, make sure it's in degrees, and you should get that this length here is 212.1. You're going to do the same thing to get your vertical component. This is your opposite side. This is your hypotenuse. So we're going to use sine. The sine of 45 will equal to, and this should say y. Our opposite side, which is y, I don't know it, over my hypotenuse, which is 300. When you put 300 times sine 45 in your calculator, you also get 212.1. Now that only happened because this was a 45, 45, 90 triangle, and these lengths are congruent in a 45, 45, 90. So that means this coordinate is at 212.1, comma 212.1. You're going to notice that we use the, I don't know what you call them, they almost look like greater than and less than symbols to distinguish that this is a vector and not a coordinate. So your horizontal component is always your x coordinate, and your vertical component is always your y coordinate. But again, we use these arrowheads essentially to show that it is a vector, and this is component form. This is not an ordered pair. So we know the head of this vector is at this point here, 212.1, comma 212.1. So that is component form. All right, example 1 says, draw a vector of vector AB, and you use that notation. It's called a harpoon to show that it's a vector. So whenever you see this harpoon over a set of 2 letters, it's representing a vector. So this reads vector AB, and it says to draw this vector AB on the coordinate plane if vector AB is at 5, -4. So it's telling you that your horizontal component's 5 and your vertical component's -4. So you would do this just like you would a coordinate. You would go right 5 and down 4, and this is where our vector is. Again, this is telling you where the head of the vector is. So that's why it said it was at 5, -4. The tail is always at the origin, and then you just draw your arrow in. So that's part B, is just labeling the head and the tail. Again, the tail is at the origin. The head is down here at this component form, 5, -4. Then it says to find the magnitude, which is simply the size of this vector. Notice you have a right triangle here, so you could use the Pythagorean theorem to figure this out. So essentially, you'd have 5 squared plus -4 squared equals the length of this squared. So you see it a lot written just like this. So instead of it saying like c squared equals 5 squared plus -4 squared, you'll just, a lot of times when you see magnitude, and you may have seen this in other classes, just go ahead and do the square root. So that's why that's there. So when you're finding the magnitude of something, it is derived from the Pythagorean theorem, but you're simply going to do the square root of whatever your horizontal component is squared plus your vertical component is squared. So both of those. So you do get the square root of 41. You're allowed to leave your answer like that, or you can round it to like the nearest 10th place. So it's about 6.4. You can also find the direction of this vector. So notice again, we do have a right triangle. We know our opposite side here, and we know our adjacent side to that angle. So we have tangent. So I can write this equation that tangent theta is equal to opposite, which is -4, over adjacent, which is 5. Remember, to get an angle, though, you have to do inverse or arctangent. So the arctangent of -4 over 5 will give you -38.7. So this angle here is -38.7 degrees. Because you're going down. So you're measuring away from the horizontal. It's going down -38.7. If you added 360 to that, you could technically say what the positive version is, or going the other way, that is 320 degrees. All right, next example, 321. It says to draw vector MN, whose horizontal component is -4, vertical component is 5. So I know that the head of this vector is at -4, 5, and the tail is always at the origin. So there's my vector, the tail's at the origin, the head's up here at -4, 5. Again, to get the magnitude, and this is just the notation, it's going to always be positive because you're talking about the size of something. So that's why the absolute values are there to symbolize magnitude. So we do the square root of the one leg of our triangle, the horizontal component -4 squared, plus the vertical component 5 squared. And on this one, you also get the square root of 41, which is approximately 6.4. Now on this one, when you go to find the direction, set up your triangle, tan theta is equal to 5 over -4. Again, to figure out the angle, you have to do arctan of 5 over 4. But when you do that, you'll get, let me do it real quick, the arctan of 5 over 4, or arctan of 5, -4, you get -51 degrees, which isn't really signifying, this angle I know is more than 90 because it's over here. So you could add 180 to get the positive version, and it's 128.7 degrees. And our last example says a basketball is shot at a 70-degree angle with the horizontal direction with an initial speed of 10 meters per second. So you could set up your initial vector. You know that from the horizontal, it has a direction of 70 degrees, and you know that the magnitude is 10 meters per second. So this is what the diagram would look like for part A. It says find the component form of the initial velocity. So whenever it is asking for the component form, it's simply asking you to find the horizontal and the vertical component. So again, we can use trig to do that. The h is our adjacent side. The 10 is the hypotenuse. So we could use cosine to figure this out. So you'd have cosine 70 equals my adjacent h over 10. When you put it in a calculator, 10 times cosine 70 is 3.4. When you find your vertical component, again, this would be your opposite side, and this would be your hypotenuse. So you could use sine. Sine 70 is equal to v over 10, opposite over hypotenuse. Plug it into your calculator. You should get that this vertical component is 9.4. To completely answer the question, just put it in component form. So remember, we use the less than and greater than symbols, the little arrowheads. And our horizontal component was 3.4. Our vertical component was 9.4. And that concludes your first lesson on vectors. The next lesson that we'll do this week will cover vector operations. If you have any questions, do not hesitate to email me, text me on Remind, or join me on Help Session. Have a great day.